Okay. Thank you, Federica, for information. Well, hello, everyone, and thank you for joining today's colloquium. This is actually the last TVS colloquium before the short summer break that we'll have, and we'll continue with our talks in September. So first of all, I would like to give a very warm welcome to our speaker today, Massimo Dall'Ora from INAF. Massimo obtained his diploma in physics in 2001 at the University of Naples, with a thesis on the variable stars in the Carina Dwarf spheroidal galaxy. And he obtained his PhD in astronomy at the University of Rome, Tor Vergata, in 2005, with a dissertation on the near-infrared period luminosity relations of the RR-Lyra stars. He is a staff researcher at the INAF Astronomical Observatory in Naples since 2013, where his current interests that are relevant for the Rubin LSST include the stellar variability, the cosmic distance ladder, and the galactic archaeology. He is a member of the TVS Science Collaboration and of the STARS, Milky Way, and Local Volume Science Collaborations since 2017. And he coordinates the TVS Crowded Field Task Force since 2018. He is also a PI of one of the Italian in-kind contributions on the variability on the crowded galactic environments, and especially of the Bulge. He has co-authored several documents related to the Rubin LSST, such as 3 white papers, the TVS roadmap, 3 Cadence Notes, and 1 research note. So today, Massimo will tell us all about crowded fields and their analysis in preparation for the LSST. So please, Massimo, the floor is yours.
Oh, thank you, Katia. And everybody, thanks for being here. And I will show you what we've done with the TVS Crowded Field Task Force. And of course, yeah. We started with the motivation to settle a crowded field task force. And first of all, a significant fraction of the Rubin LSST data will collect in very dense crowded environments, and in which we expect to get a lot of information on the history of the galactic formation, the structure of the galaxy, and the distance scale, and to whatever. Data, of course, will be of unprecedented quality, depth, and we will get a lot of variability information on stars, galaxies, and so on. And but the problem is that we should need in advance how to afford such a wealth of information. And additionally, there is some interest from some international in-kind contribution in offering analysis techniques and software with ad hoc simultaneous wavelength photometry and code for stellar variability analysis. And because of this motivation, we started in 2018 with this task force by focusing on a bulge dataset. Here is some info of the people involved in the TVS Crowded Field Task Force. Here's the contact. Kelly is our spokesperson, and this is our Slack channel. So, what we focus on so far, we got in a few slides. I will show you. Will present you the data set, and we started with some precision PSF photometry in crowded fields, and we performed some forced photometric experiments. At the same time, with this photometry, we focused on the variability search, period findings of the candidate variable stars, and some cadence experiments. And all this stuff is going to be used for a cross check with the DIA objects, with the socket catalogs, and with the exploiting of the science platform. And at the very end, our goals are to gain expertise on all of these topics, to provide community with our feedback and sharing with our code expertise and know-how. So let's present the dataset. The dataset, we found some DACAM calibrated archival images. The PI is Abisa. And this is quite interesting because more than 50 euro per band with bands with exposure times between 10 and 300 seconds in 5 photometric bands. And the project was designed to detect area stars. So this was quite interesting. But also in the same areas, we have the results from the Augur4 catalog. So we know several variables, and so we can compare our results with the results taken with Augur, and also we can calibrate our photometry with the local standards coming, for example, with from DACAM plane surveys with DACAPs. So this is the area that we chose it, and of course, this is a lot of images, so we identify a subset of only 150 mosaics, but we were not interested in reducing all of them, so we just focused on a single, at the very end, a single CCD, a single chip of the mosaic, where was contained the Bulge Globular Cluster NGC 6569, and this is the field N19 in this picture, this one. So we adopted a completely blind analysis approach in the sense that we perform a complete DO photo star frame PSF reduction with the fully automated PSF photometry, we shall check of the stars, just a few scripts to automatically discard the outliers. There is a little warning because this data is not exactly a proxy of the Ruby and SSD data, because data have been collected in a few nights in 2 separate runs with a gap of approximately 2 years. So it's not a continuous spanning of the field, and also exposure times are not uniform, but they have a range from 10 seconds to 300 seconds. And the variability was done automatically for example, the spread of the photometry with some variability indexes and fast Fourier transform. And then the periods were searched with FFT in more specifically with the Lomskargol algorithm, and we cross-matched with our results with the Augur. Then we go ahead with the manual check of the light curve. So this is our all-frame photometry. This is just, I stress again this point, just one chip of the mosaic. This is a color magnitude diagram, and color-coded is the photometric accuracy. And this is what was published for a whole mosaic in a nearby region. So the depth, it's very, very similar. Here you see just instrumental magnitudes. Basically, you have to have the 5 magnitudes to get the calibrated magnitudes. So basically, you see that we, even with a single chip, we had a lot of statistics and the same photometric depth. So let's start with the variability. We started with adopting some variability criteria, for example, using the BUS software, and we had in our catalog, starting from more than 140,000 stars, we had 10,000 candidate objects. We performed a Lomskargol analysis, and we cross-matched these results with the photometric quality given by your frame. And again, we cross-matched with, for example, the shape parameters of the photometry and with the Stetson variability index. At the very end, we had about 2,000 candidates for which we produced individual light curves that we visually inspected. So this is just a small compilation of course, of the best candidate variable stars. You can see several allied stars. You can see, for example, eclipsing binaries, and here you see specifically weird objects, and I will discuss this object in a few slides. It's important, the classification for these objects, because a correct classification depends on a successful period search. For example, an eclipsing binary can be misclassified as a first overtone allied stars, or vice versa. So basically we need colors to put the variables in a color magnitude diagram, but also we need reliable periods. And according to our experience, the best way is to experiment different algorithms for different classes of variable objects. So on this aspect, it's very interesting, the experience coming from, for example, ZTF, where they use a hierarchical approach. For example, they use at the same time two different introductive algorithms. One is the conditional entropy, and this is good, for example, for long periods, but also for eclipsing binaries. And Lomskargol is good for short periods, especially delta Scuti and RL stars. They provide some input frequencies for a more refined analysis with, for example, with the Schwarzenberg-Czerny algorithm. So we did something similar in our task force. For example, this is the same Alaria stars inspected with the fast Fourier transform, with the phase dispersion minimization and with the Lomskargol. And you see that the results can be completely different according to the algorithm. We also experiment our own algorithm. Basically, it's very similar to PDM, with a derivative on the spread of the points in the phase magnitude plane. And again, this is another RL star, and again PDM and a simple FFT completely fail in finding the true period. Lomskargol also fails, and our algorithm is completely fitted to find the correct period. So we just focus on Ogle variables, and the Lomskargol sets power spectrum versus the Stetson variability plane. We found it is a useful tool to pinpoint good candidates. For example, here you see in green the Ogle variables, and you see that most of them are characterized by high values of the Lomskargol power, but also high values of the Stetson variability index. And this is, for example, good to get an estimate of the completeness of our sample and the contamination. So these are our results with Ogle. In the field, there are more 117 objects from Ogle, the Ogle catalog. These are the census, RL stars, eclipsing binaries, ellipsoidal variables, CFITs, delta Scuti, and this is what we found. We were able to retrieve most of the objects, and several of them were cut by the VAST software, in the sense that the VAST wants a minimum number of photometric measurements. I think it's 10 to start the variability. When you have less than this number, the study is discarded from subsequent analysis. But in some cases, where also Lomskargol failed to get the correct periods. For example, this is a typical epic fail. This is a bulge Alarial star. This is the power spectrum. This is the phase of the light curve, but, and of course you don't see anything relevant here, but if you check the time domain light curve, you see a clear sign of variability. And fails, we found that where fails are typically with variables whose periods are masked by aliases. In this case, we have the period is very similar to the half-day alias. So it's quite difficult for Lomskargol to correctly find the period. And again, this is a previously unknown object, and therefore a candidate in variable star. Again, Lomskargol completely failed in finding the true period, but again, you see the correct, that the time domain light curve is strong. So this is definitely a good candidate variable star. Some science with this data. This is the period luminosity relation in the Z-band. I think this is the first one for Alarial star belonging to an individual globular cluster in this photometric band. And this is our estimate of the slope and the 0 point. This is the instrumental 0 point. The absolute 0 point is not available from the literature, and we'll try to refine it with the Gaia. But in any case, we are happy with the slope because this is what theory predicts here, and at this wavelength. And also the root mean square and the dispersion is quite small. So we are happy of this result. Again, some science. This is the strange case of Alarial star, in the sense that in 3 bands, the photometric light curve was quite noisy, but for example, in the Z band, you clearly see 2 different light curves. And this is the sign of a possible phase modulation. We discussed along this star within our task course. At the very end, we decided to compare our photometry with the photometry provided by Ogle. Here you see the Ogle photometry, and within a given range of Julian days. This is our photometry in the same range, and this is the green, and in green you see our photometry, but outside. Remember that our data were collected with a time gap of 2 years. We measured the shift in phase, and once that we account for different phase shift and photometric shift, the light curves can be are very similar. But again, if we use for example, the Ogle period, we see that something strange happens here and here, in the sense that the period seems not really the true period. And so again, we decided to study separately the 2 data set, and the one collected in 1 year and the other one collected after 2 years, and we found 2 frequencies slightly different, but significantly different, in the sense that the difference was larger than the errors. And so we extended this analysis with the Ogle data because the Ogle data span more than 1,400 days, and what we found is was a clear trend. The period, the frequency is increasing, and this means that the period is slowing. So this is probably an evolutionary effect. So we are happy because this is exactly what we expect when with the Rubin LSSD data after 10 years, we can found this kind of results. We also made some experiments on the cadence. For example, waiting for the survey, the Rubin survey, what is the minimum of epochs to get reasonable periods, and this means mean quantities. what is the confidence of this the measured quantities, mean magnitudes, amplitudes, and so on, and what is the dependence on the period and on the variability type, and also what is the dependence on the passband. So we started for our observed light curve, and we just simulated starting from the observed light curve in the phase magnitude and plane. We extracted the random points simulating the time domain, the time strategy of the wide, fast, and deep survey. So we wrote a code to do this, and we ran a period-defined code on the simulated time domain light curves. And we just compared our results with the estimate periods with the two one. Of course, the experiment was made for all our stars in our sample several times. So we have a distribution of the residuals between the estimated periods and the true one. And this is a measure of the robustness of the period after a given number of measurements. So these are, for example, a plot. This is for just 15 epochs with a 20 days cadence. 20 days cadence is more or less the same, is the wide, fast, and deep cadence, but with different filters. So if we go in the same field with the same band, with 3 days cadence, we can observe the same object after 20 days. And for example, this is for the short periods. Even with the 15 epochs, residuals are very, very small. So with, for example, sinusoidal light curves, 15 epochs is definitely enough to take the correct periods, regardless of the photometric band. Things, of course, are much worse with periods where we are dominated by the dialysis, or for long periods. And this is the same for 30 periods. And of course, with 30 epochs, we have better results. Again, we asked ourselves what is about the impact of accuracy of the periods on the mean quantities. We started with a variable stars with a true Auger period, and we just adopted a wrong period, and we computed again the mean magnitude. Here V is R, so please do not focus on the name of the magnitude. And again, even with the wrong period, so with a wrong phasing of the light curve, for a short period variable, the mean magnitude, here the averages in magnitude and intensity are very similar, within 1/100th of magnitude. The same with an AB type star with an asymmetrical light curve, and again we get good results even if here the mismatch is of the order of 0.05 magnitudes. Moreover, what is the impact of the signal to noise ratio of our measurements on the periods? For example, what is the impact of the photometric uncertainty on the determination of the periods? And so starting from our likes, we added up to 0.1 photometric noise to individual measurements on same star variable stars. Data were processed again through a Lomskargol period search. And here, what we, for example, is what we get for one of them. The first number is the peak of the power spectrum, and of course, it's better with the good measurements. But the second one is the period, and you see that it's absolutely the same, even with the noisy light curves. And we just made one test on a symmetrical light curve, and we will make an extensive analysis. Just to show you graphically what we did, this is the true Auger period with the true photometric noise. This is the same on the right with the higher noise. We added the 0.05 magnitudes, and this is the difference between the average magnitudes in the true case and the noisy case. And you see that the numbers are absolutely the same, but also when we reach a higher noise with the 0.01 magnitudes, numbers are basically the same, even with an asymmetrical light curve. Again, we focused on the cadence. And here, for example, we measured the residuals between measured and true magnitudes in different baselines as a function of different baselines. Again, the filters are color-coded and the numbers are sum of the available baselines. And you can find the details in the Cadence Note wrote by Ilaria and other colleagues. And after 2 years, again, you see that the difference in magnitudes are almost negligible for most of the baselines. These are the results after 6 years, and this is what we get for Cepheid stars after 2 years, and after 6 years. So basically, for Cepheids, we have to wait a bit more to get reliable results, and this is what we get for long period variables after 6 years. Also, speaking about Cadence Notes, we focused on the fraction of the bulge that we can reach with RLS stars to get distances and individual metallicities. And the requirement is that we need a maximum photometric error of 0.04 magnitudes on all the available bands, according to the prescription from the paper published by Bon et al. 2018. And here the error is measured as a difference between the true and measured magnitudes. And this is, for example, the fraction of the bulge that we can probe with RLS stars to use them as a distance indicator, but also as a population tracers, in the sense that we can get individual metallicities for the bulge. Details are, you can find the details in Cadence Note wrote by Will Clarkson and other colleagues. And this is the volume to precision plot as a function of the difference baselines with available in the database. So what is, we have a number of variable stars, but we are going to find variables according to the LSST, Rubin LSST ALES stream. So we were particularly interested in this document published this year by Jan Salleman and Eric Benm, where they announced the availability of some DECAM bulge fields reduced with the Rubin LSST DIA analysis. They kindly provided us their results, and we are going to compare their results with our variability search. So when the telescope will be on the mountain and the data will start to arrive to be measured, to be analyzed by the community, basically we will rely on LSST alert production. But in a second stage, we will have the problem to classify and correctly get, for example, the periods and mean magnitudes of the periodic variable stars. So here we have a strong benchmark to compare the first alert production results with what we already know from the same field. Let's move to the static science. As I mentioned at the very beginning, the field contains also the very dense globular cluster NGC 6569, and this is a very interesting benchmark for very, very dense crowded area. And there is also some scientific interest because this is the first UG-RIZ available photometry for the cluster. This is heavily contaminated by the field. And of course, on the cluster, we had a lot to experiment and learn. The first problem is just because of the contamination is the splitting of the cluster stars from the field stars. And Gaia is not deep enough to clean up the catalog. Here you see a comparison with the DDR2 data, but the situation does not change very much with the new EDR3 data. And even with the standard color diagram selection, we cannot effectively disentangle field stars from cluster stars because the metallicity is quite the same. And also a standard heuristic approach on the sky position is not really effective. So we started to think about a multi-band approach. Actually, it was already devised and published, for example, in these two papers. And we just used a kind of three-dimensional color magnitude diagram. Here we have R versus U minus G versus G minus R. And for example, this is for the cluster M71. And with this approach, we can effectively, as you can see in this plot, disentangle the cluster stars from the field stars. We used the same approach, and results were not really very, very good, but we, in any case, we were able to clean the color magnitude diagram from the field contamination. And again, we can show you some science. For example, a combination of color indices to disentangle multiple stellar population in a given globular clusters. You know that several globular clusters host different stellar populations. And for example, U minus B color index is sensitive to the light elements variations, as discussed, for example, in these papers. And the B minus I color is sensitive to helium variation. So Matteo Monelli proposed to use a combination of these two color indexes to maximize the differences in helium and light variation. And this method showed to be really useful to split multiple stellar population in star clusters. But this is for Johnson filters. So the question was, will a combination of the similar filters, but with the LSST filters, will work as well? Here I show the sensitivity of the various elements to the passbands, and the answer is yes. For example, you can see here the plot of the R magnitude versus the combination of the U, G, and I bands, with superimposed a Bassi isochron with this metallicity and with this alpha enhancement. And of course, the isochron is a very standard isochron, so you just see the normal red giant stars, but all the stars that are off this position are, for example, cyan enriched or helium enriched giant stars. So this index effectively works in disentangle different stellar populations. This is I think, an important problem that we are going to face not only in the galactic bulge, but for example, in the galactic disk everywhere in the galactic plane. Here you see a standard color magnitude diagram with superimposed an isochron, and the magnitudes were corrected for reddening with the standard, let me say, Schlegel map, the Schlegel correction, and the agreement is not quite satisfactorily. And here you see the same, but the isochron was reddened with an ad hoc reddening correction computed on the basis of the RL stars properties in the field. And here the agreement is much better. And we think that there is a problem with the reddening, because reddening is usually estimated from the Schlegel maps, even with the new calibration. And again, this is the same as before. We compared the sub-CMD, where individual stars have been corrected for the local reddening with a Bassi isochron with these features. And we adopted this average section. This is the same as discussed in a very nice paper by Saracino et al. And local extinction, where we adopted local extinction published by the BDBS and kindly provided us by Christian Johnson. And again, the agreement is not good. But if we use the same approach adopted in Ortolani et al., we found a higher reddening law and different distance modulus. So where is the problem? It is a problem with models, and this is, we think, unlikely, because different families of isochrons give similar results. It's not only a problem with the Basti isochron. Using different models, as discussed in Saracino et al., with a spread of just 100 of magnitudes, both in distance and reddening. These are, for example, the numbers that you get with different sets of isochrons. Give the same numbers, and they are also in agreement with other CMD morphological based techniques. And the same models, for example, perfectly work with the yellow clusters, where we have a different situation with the reddening, because there is a very low reddening. Here, the key point is that stars trace the total reddening up to their location. So they are just telling us, okay, this is the reddening that you see in our position. But when we use, for example, the Schlegel maps, they originally were derived from the dust far infrared emission, even with the new stellar calibration published in 2011. And as you can see in the plot, published in the paper by Schlafly and Finkbeiner, there is some deviation from the extinction between the two reddening, the two calibration as a function of at different galactic latitudes. And we discussed these points even, for example, with Leo. And probably the idea is that we definitely need three-dimensional extinction maps. Just to end my slides, it was published last year a catalog, a document where a forced all-star photometry was proposed in very dense environments. And basically, they start with the usually LSST pipeline, but at a very at a given point with the crowded field, they adopted a simultaneous PSF fitting only on relevant areas. And here for simultaneous, that should mean that the same master list is fitted on individual images. This is a bit different from our approach, your frame approach, because here in our approach, simultaneous means that the positions and fluxes are simultaneously cross-correlated on all the available images. And of course, the difference, the approach is completely different, and the frame approach is really, how can I say, computing time extensive. Our approach also can allow us to find objects even in the very center of dense globular cluster. Here again is the globular cluster NGC 6569, and the red dots are the sources that we found with our frame approach. But we are definitely convinced that the blender, for example, Scarlet, will do a great job in these particularly dense areas. We started with a series of tests on the standard forced photometry, and we compared these results with our frame catalogs. And here you see the all-star approach and blue-green, two different frame approach with different number of iteration. And the first glance, but we have to confirm these numbers. All-frame photometry seems to achieve more accurate and deep magnitudes than individual images or star. But we need to perform a full forced photometry analysis. Our procedures are still running, and here we compare a CMD obtained with a couple of GR images with all frame and with the all-star forced photometry. And this is the standard all-star forced photometry approach. And this is what we get with the all frame. What is the problem? The problem is that to perform a complete all frame analysis, basically is needed a prohibitive computing time for probably for the LST schedule for the timeline, and maybe this could be afforded by international in-kind contributors. So this is just a suggestion. We have to face some problems, since here you can see the run of the residuals between our frame and the forced photometry as a function of the frame magnitudes. And we see a clear trend at the frame magnitudes between our star and our frame. The reason for this behavior is still to be investigated. And this is, as you can easily imagine, absolutely relevant for population studies at the detection limit. So we have to study this problem. I will end up my talk with the start of our place with the science platform. Sarah is taking care of this. So we uploaded our catalogs on the Rubin Science platform, and we started to write some Jupyter notebooks and tools to effectively analyze the data. Here again, you see a color magnitude diagram on the basis of the Gaia proper motions. Experiments are still ongoing, and specific notebooks are being written. A paper is in preparation, and I will end up with my takeaway messages. Our CrowdFit task force is active since 2018, and we tried to face all the peculiarities of the data analysis in such stellar crowded areas. We strongly encourage the adoption of PSF photometry and ad hoc techniques and algorithms for different classes of variable stars. And in our opinion, first robust results on periodic variables can be achieved even after 18 months from the beginning of the survey. Great will be the synergies with Gaia and other surveys, for example, OGLE, ZTF, and so on. Reddening is an important issue in the galactic plane and bulge and should be addressed carefully. And in particularly crowded areas, the blenders like Scarlett can make the difference. Again, here are our contacts. And please don't miss the PCW 2021 session devoted to stellar crowded field, organized in synergy with the Stellar Crowded Field Task Force of the Stars Milky Way Local Volume Science Collaboration. Thanks for your patience and time. Thank you.
Thank you, Massimo. That was a really nice talk. Do we have any questions? If you have any questions, just raise your hand. Meanwhile, okay, Federica has a question.
Hello, Massimo. How are you?
Great, Federica. Nice to see you.
Nice to see you too. Thank you for the talk and for leading this task force for a long time now. So thank you so much for that. It's been a core effort in TVS, and it's really great to see this. So the OPSIM, the Rubin, sorry, not OPSIM at all. The Rubin data management team is working on the definition of the time series features that will be included in the alert packets. And I'm wondering if it is worth thinking about these time series features specifically, thinking about their performance in the crowded fields, and having a specific discussion to see if the features as they are planned or as they are suggested with the contribution of the rest of the community do fit the needs of galactic plane and crowded field science.
Okay, this is good to know. Of course, we just focus on periodic variable stars, and for the periodic variable stars, you basically need the history of the light curve. So definitely a broker system, for example, the Alice stream that will feed the broker system, and the broker system should have memory of the history of the light curve. And probably, again, our feeling is that different algorithms will manage differently well different kind of variable stars. And we should also mention the not periodic variable stars. And in our field, we have the feeling that there are a lot of non-periodic variable stars, or with the periodicity which is outside the range of our time data set.
Okay, thank you. There is another question from Leo.
Hi, Massimo.
Hi, Leo.
Okay. Can you hear me? Yes. Okay. I have a question. It's not exactly for you, it's for everybody. Is regarding the extinction maps. I completely agree that we need 3D extinction maps, but I have no idea of who will give us these 3D maps. Do you have an idea?
No.
In my opinion, the best people for doing that is the Pan-STARRS team, who has done these beautiful 3D maps based on Pan-STARRS plus 2MASS plus Sloan photometry by Green et al. But I have no idea if they are involved in LSST, or I think they are not exactly in this moment involved in LSST. So if anybody has any idea about that, please tell us.
But their method was fairly openly described, right? So in principle, it's possible to adopt, and I think maybe even the code. So it's it's possible to adopt.
Yes.
And it would be a really good thing for some people in the science collaborations to think about. perhaps test
Yeah.
it, right?
Yeah, I think it can be used, but somebody has to take charge of that, of course. It will not happen if nobody is working on that.
Yeah, of course, with very, very specific areas, for example, around globular clusters which is full of RR stars, of red clump stars, so you can use stellar tracers to model the local reddening, but you know, this is just a tiny fraction of all the whole bulge and the whole galactic plane. So basically, this is what I was pushing for general three-dimensional extension maps.
Okay.
Yeah.
Okay, do we have any other question lined up? I don't see any. I just have a short, probably very easy question. In the beginning, you were saying that you need colors to differentiate between different variables, if I understood correctly. So what are the best combinations of filters that you might want in the LSST cadence?
Probably depends on what you are looking for, in the sense, if you were, for example, I'm sorry, I always talk about RR stars, but you know, I live with RR stars from 20 years, and probably the optical bands G and R are the best, because we have the best way to find the variability, because the excursion in the light curve is quite high, and also they populate the horizontal branch in a globular cluster, so they are quite easy to pinpoint. For example, some eclipsing binaries or some delta scuti, well, long period delta scuti could have similar periods and similar shape in the light curve of some first overtone RR stars, but definitely their position in the color magnitude diagram could be it is different. So this is why I stressed that colors are useful to classify variable stars. For example, again, you can use the period luminosity relation of RR stars of other kind of variable stars, for example, Cepheids or Miras on whatever, because colors can put your variable star in a different relation. So you can disentangle a possible object with a true object in a period luminosity relation. I think that Ilaria is an expert, for example, on Cepheid stars, and can discuss this point much better than me.
Okay, thank you.
Thank you.
Do we have any other questions? So I don't see any, and therefore I would like to thank again Massimo for this very interesting talk. Thank you everyone also who attended, and I'll see you in September for our next colloquium. Bye.
Thank you.
Bye bye. Thank you.
Bye.